hopefully will. Okay, today we will learn a what we call okay today, and please guys, stop me at any time. Don't feel as if, you know, like, don't be embarrassed that you might not understand something. I'd rather you ask me and we can go over it, because most likely a lot of your classmates probably have the same question. And so today we'll learn the principle of superposition, okay? And it's a nice little way of being able to solve situations. And I think this is going to be the, okay. So determining the deflection of beams using the principle of superposition. Now, we can do this for deflections, we can do this for moments, we can do this for shears, but we'll apply it to deflections, okay? Now, if I have a beam, okay, if I have a beam and here the beam's got one load here, it's got a uniformly distributed load here, it has a concentrated load there and a concentrated load there, okay? Now, if I can determine the deflection caused by the uniformly distributed load, and if I want to calculate the deflection at this point here, and that's where we normally want to calculate the deflection, this is called midspan, okay, L over 2. And at the same point here, I can calculate the deflection caused by this concentrated load. And at the same time, I can count at right at the same point here, I can calculate the deflection caused by this load. Then if I want to calculate the total deflection, I simply, once I've calculated the first one and the second one and the third one, the three of them added together will give me the total deflection that the beam is going to undergo, okay? And of course, this is where you're always looking at the same location. So for example, if I wanted to calculate the deflection at this point here, then I would have to calculate the deflection at that point there, and I have to calculate the deflection, and then I would be able to, and that will give me the same value there, and so on and so on, okay? Now, the way this applies for deflection, this also applies for moment. So for example, if I calculate the moment at this point, and I calculate the moment at that point, I calculate the moment at that point, the sum of those three moments are going to be the same. That's what you're going to get as a result of all these loads. So this applies to moments, applies to shears, applies to deflections, okay? As long as you stay what we call, as long as you stay within what we call the elastic range, okay? So the elastic range means that you will not go beyond the yield stress of the material that you're using for your beam. So the resulting stress or strain in a system due to several loads is the algebraic sum of their effects when separately applied. So that's why you can also use it for stresses, in other words, for forces, you know, bending moments, shears, and so on. So as long as you stay, the superposition principle is applicable only in the elastic range of materials where deformations are small, okay? Because when you get into the plastic range, it's completely different, and therefore there's no stress-strain relationship at that point, and therefore you can't apply this principle. But in theory, whenever we are designing a beam, okay, we always want to make sure we stay in the elastic range. In other words, we don't exceed the yield strength of the material, and therefore we can use this principle to help us figure out something, whatever we need to figure out for our structure. Now, okay, so the best thing to do is I'm going to show you how you apply this to an example, and this way you'll be able to relate to it a little bit more. Okay, now here I have determine the deflection at midspan. So I want to determine the, like, midspan is here at 3,000. I want to determine the deflection at midspan. Okay. And when we talk about deflection, we always represent deflection with this Greek letter called delta, okay? So at midspan, in other words, we want, okay, the uniformly distributed load, in other words, this one here, okay, does not include the self-weight of the beam, okay? So we have to add the self-weight of the beam to this load, okay? Now, the steel beam is a W310 by 39. Now, I know you guys haven't done any, I'm pretty sure they don't do this in construction 1 and construction 2, but I will explain to you what this means, okay? Whenever you see the first letter in steel represents the shape of your profile. So when we're talking about W, we are talking about wide flanges, okay? A wide flange looks like an I, or some people like to call them H's, okay? But we call these wide flanges. I'm pretty sure you've all seen this type of beam, okay? So that's a wide flange. So in other words, as soon as I see a W on the drawing, in my mind, what I see is this cross section. That's number one, okay? The 310 means that this beam will weigh 310, I'm sorry, the 310 is the nominal depth of the beam. In other words, this beam will have a depth of approximately 310 millimeters. The actual depth, you can get it from the table, but it gives you an idea that it's, so this is, of course, this is metric, and therefore this is in millimeters. So therefore this has a depth of about 310 millimeters. If this was an imperial designation, this would have a depth of 12 inches. That would be the imperial one, okay? And the 39 means that this thing weighs 39 kilograms per meter. So this is the mass per unit length, this is the nominal depth, and this is the shape of the beam. So that's, okay? That's what these three things designate. And when you see this on a structural drawing, in other words, you can have, for example, a C, which represents channels. You can have a T, which represents T's. You can have a, okay, so you have different letters that represents different profiles. And then after that, these numbers represent some other information. Like I said, for a wide flange, this represents the nominal depth, and this represents how much the mass per unit length that this thing is going to actually end up weighing. So that means that I would have to take this 39 kilograms per meter and add it to the 20 kilonewtons per meter to get the total weight, okay? Now, the reason why I say IX, okay, the strong axis, because when you have a steel beam, okay, and we're going to be doing some, I think next week when we talk about cross-sectional properties, okay? The cross-sectional properties of a steel beam, we represent this as being the X axis, and we have here the Y axis, and therefore the moment of inertia with respect to the X axis is much stronger than the moment of inertia with respect to the Y axis, and then we tend to call this the strong axis. So therefore, the moment of inertia is what's going to be contribute to the stiffness of the beam, and the higher the moment of inertia, the higher the I value, the more stiffer, or the less it's going to deflect. So if you want to control deflection, you pick a beam that's got a very high moment of inertia, okay? And in this case, we say that the moment of inertia here about the x-axis, because we will always put the beam spanning this way, and we'll always make sure that the x-axis is, okay, perpendicular to how we're applying the load, okay? And that's how we normally place the beam. So we always place a strong axis perpendicular to how the loads are being applied to the beam, so that we can control deflection. And also at the same time, it also, anyways, I won't get into that right now. We're not here to teach a steel course. Now, this here, 200,000 MPa, okay, everybody, do you guys remember the modulusicity? Do you guys remember what that is from your physics class? If it's, say yes or no, let me know. Because I'm just assuming that you guys remember what the modulusicity is. Does anybody remember?
Please explain it.
Can we explain it? Did you see this? Did you see this in your physics class where they showed you this graph? They showed you a y-axis, and then they showed you an x-axis like this. And here they put stress, and here they put strain. And they said for steel, the stress-strain relationship, it looks like this. Did they show you this graph in steel? In physics, they show you how the stress and the strain are related?
Yeah.
Okay. Well, in this range here, okay, stress over strain is equal to the modulus of elasticity. Okay, it's the relationship of the stress with the strain. In other words, as I increase the stress in the beam will strain. In other words, will have more deformation, and therefore it will, okay? And as long as you stay within this range here, we call this the elastic range, okay? If I put a load, it should come back to zero, you understand? So the modularity is the relationship of how much deformation a material will go based on the amount of stress that it's going to be subjected to, okay? And then up to the yield point here, okay, this is called the yield point. The stress strain, well, you consider it to be, like elastic. So this is the elastic range of the material. Then after that, it starts getting to what we call the plastic range. The plastic range that it's going to deform. If you take off the load, part of that deformation is going to stay and become a residual deformation in your member. And then after that, if you keep straining it to the point that you get here, well, it's going to break. Okay, so this is called the elastic range here, and this is called the plastic range. Plastic range means that deformations will occur, and if you remove the load before it collapses, those deformations, whatever deformations it incurred in that range, it will stay permanently deformed. Part of it will come back, but a lot of it will stay deformed. And what happens here is that when you get past the yield point, what they're showing you here is that as you add less strain, you get lots of deformation. In other words, the material starts to stretch, starts to become almost like plastic. So it's going to be very, 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 stretch and big deformations. So for steel, what we're saying is that if I have a certain amount of stress and I want to calculate the strain, well, the E value for steel, we assume it to be 200,000 MPa. That's what that value is. So whenever I want to calculate some strain based on the stress it has, or if I know the strain and I want to calculate the stress based on this E value, I can calculate either one of them. So this is stress over strain is equal to your modulus of elasticity. Okay, and that's what that is. They covered this in physics, right? Did they talk about this in physics at all?
Yes, sir.
They have, right? I don't know if they still. Do they have any labs on this at all in physics, or how did they present it? Okay, is that? Does anybody have any questions before I go on? So basically, if I want to calculate the deflection for this problem here, okay, so like I said, what I need to do is I need to calculate the self-weight of the beam. And I know that 39 kilograms per meter, and if I multiply by the force of gravity, right, and of course I have to divide it by 1,000 to get into kilonewtons, that's going to give me the actual force per unit length, okay, of the beam. So this ends up being 0.4 kilonewtons per meter. And of course, add the self-weight to the beam, I end up getting 20.04. So that would be the total uniformly distributed load across the beam, okay? Now, so what I want to do now is I want to be able to calculate the deflection that this beam will undergo based on the fact that it's going to have to carry a uniformly distributed load, including the self-weight of 20.4 kilonewtons. Now, how do I do that? Well, in many textbooks, okay, in many handbooks, you have, okay, determine the deflection caused by uniformly distributed load. In many textbooks, you have what they call beam formulas and beam diagrams. And these are very, very useful in doing certain calculations that it simplifies the analysis we need to do. And I'm going to show you what these things look like. Like you're going to get, you're going to get the lecture at the end, okay? So I'll just go through this very clearly, okay? So this is what they call beam diagrams and formulas. The reason why the beam diagrams means that, I'll start at the very beginning. Beam diagrams and formulas, okay? So here, they're showing you a diagram, and if what you're analyzing corresponds to exactly what your diagram looks like, then you're allowed to use all the formulas that you have here to determine whatever you need to determine regarding this beam, okay? So here, for example, this is simply supported, and if I have a uniformly distributed load going right across the whole span, then based on this diagram, I'm allowed to determine what's going to be the reaction here, okay? So the action is simply WL over 2. L always represents the span. X represents a distance from one of the reaction areas to anywhere along the beam. And of course, this is L over 2, L over 2. Here they're trying to show you where the maximum moment will occur. Okay, so if I want to calculate the shear anywhere along this beam, I simply use this formula here and I'll be able to calculate the shear anywhere along this beam. If I want to calculate the maximum moment right here based on the fact that I have a uniformly distributed load going across the whole span, well, the maximum moment will be WL squared over 8. So therefore, instead of me having to do a bending moment diagram, if I have a simply supported member and I need to design it, I need to know what the maximum moment is going to be. I will calculate that using WL squared over 2. If for whatever reason I need to calculate the moment anywhere else in the span, I can use this equation here. And of course, if I want to calculate the deflection, the maximum deflection will occur at the center. So the maximum deflection will occur at the center, and therefore that's equal to WL, 5WL to the fourth over 384 EI. So this is the formula that will give me the maximum deflection at the center. And if for whatever reasons I want to calculate anywhere else the deflection, well, this is the equation I have to calculate deflection. So these are very, very practical. So if I happen to have a triangular load, so for example, if I'm doing a roof structure and I know I'm going to have a triangular load, I can come and use, if I have a triangular load on my beam, I can use all these formulas here to do whatever I need to calculate. So if I want to calculate deflection, I want to calculate moments, I want to calculate shears, all these equations here. The only thing that this one has, you'll notice that here you have a small w, here you have a big W. A big W means that you calculate the total weight that's occurring in this triangle, and that's what you use in the formulas. So the W represents, for example, the total weight. So the total weight, the W here, would simply be equal to your L times whatever load you have there divided by 2, and that's your, and that's what you use in these equations. So that's what they have there. Now, the other thing is that there are situations where the load on your beam can be this type of triangle, and I can tell you where that can occur, okay? There's very, like, for example, when you're stockpiling a granular material on a floor, it's very likely that it's going to have one of these triangular shapes after it's been stockpiled, and therefore you can use this to calculate whatever you need to calculate for those beams. And this becomes a shear diagram, and this becomes the moment diagram. And I can use all of these equations here to do whatever I need to do in order to do the analysis of my beam. If I want to calculate moments, if I want to calculate moments at a certain point, if I want to calculate deflections, and so on. So the only thing you have to be careful about when you want to use these tables is that whatever you want to use to analyze, okay, and what you have to make sure that it corresponds to exactly the diagram you have here. So for example, on the next one, so this is if I have a distributed load and it's somewhere along the beam, okay, then I can use this one here to do all my calculations. If I have a distributed load, but it's only on part of the beam here on one side. So for example, if I happen to have, if I happen to have a load here like this and it doesn't go all the way across, then I can still use this as long as it doesn't go across. If the load goes all the way across like this, well, I'll use the first diagram because it's going to be much easier than using all of these equations here, okay? Now here they're saying if I have a distributed load here, but it's higher than the distributed layer, and I have it on 2 sections, I can use all of these equations. So as long as whatever you have in terms of a load diagram that you want to analyze, if it corresponds to the diagrams you see here, you're entitled to use all the equations you have here to do your analysis and to do whatever calculations you want. Now, the only thing that you have to be careful about is here you have, for example, you have A, you have C, okay, you have B. So you got to be careful about making sure that whenever, like for example, when X is greater than A, so you have to be careful on the restrictions and when you can use these, okay? That's the only thing. But other than that, if you conform to the restrictions, whatever values you get from these formulas, they're going to be the same values that you would get if you spent $4,000 on a software. They're going to get the same answers. And that's what's nice about this, is that you don't have to spend $4,000 for your software. You can do a lot of analysis based on these beam formulas that can save you a lot of money. Now this one's nice. For example, sometimes it can happen you have a simply supported member with just one concentrated load. Well, like it's very simple, but still, I want to calculate a deflection caused by that. Well, here's a deflection. So if I know that, for example, like if this is P, then the reaction here is P over 2, P over 2. And I know that's also equal to the shear here, P over 2, P over 2. And if I want to calculate maximum moment here, that's PL over 4, PL over 4. And if I want to calculate the deflection at midspan, so here's the equation for the deflection at midspan. But this means that there's only one concentrated load, and it falls right in the middle. So L always represents the excuse me, represents the span of your member. Now, if I happen to have a concentrated load here, and it's not in the center, then I can use these formulas here, but I have to be careful because here it says that when I want to calculate this deflection, the value of x here, in other words, the distance where I'm calculating my deflection, has to be less than the value of a. Okay, so that's one of the restrictions. So, and so on. And then if I have two concentrated loads that are equally spaced from the reaction areas, which is very typical. For example, whenever I have very typical that I can have a beam here and a beam here, and it's being supported by two girders. Well, those two beams on this girder here, this is the girder, and those two beams will give me two concentrated loads, and therefore I can determine the load there, and I can use this. This is what's, and then I can come to this one, and I can calculate all my moments, all my shears, all my deflections based on the fact that I have all these formulas. So that's a very typical situation in structural steel. And then of course it keeps going. Now here, if I have excuse me, I have two concentrated load, but they're not equally distanced from the ends. One happens to be different from the other, then I would use this diagram here. Okay, and here all of a sudden, if I want to know the values in between these two, then I would use this diagram here. Okay, now if I happen to have a fixed beam here, this is fixed, but it happens to have supported on one end, I can use all these equations here. So that could be another typical situation you can have, and so on. So now this is like I have a concentrated load in the middle, I have a concentrated load anywhere acting along the beam. I can use all these equations here to do my analysis, to do whatever I need to do, and so on. And of course, this is fixed. These become statically indeterminate, and therefore, even though they're statically indeterminate, I can use all these formulas to calculate my moments, my shears, my deflections, and so on. And whether it's a uniformly distributed load, whether it's a concentrated load that's not at the center, and so on. If I happen to have a triangular load on a cantilever, I can use this to calculate anything I need. If I have a uniformly distributed load on a cantilever, I know that this is statically determined, but if I want to calculate a deflection, instead of me finding, there's very, very complicated I come here to calculate the maximum deflection, delta, okay. So delta max is at the free end, therefore I can simply use this equation to calculate the deflection caused by that load, and so on. And then if I happen to have a moment at the end of my cantilever, well, these are all the equations I can have. Like people say, how can a moment be caused at a cantilever? Well, if ever you happen to have, if you happen to have a, if you happen to have a beam, and on that beam you have some kind of and there's a wind load here. I'm sorry, and there's a wind load. So instead of, what you do is you calculate the moment that wind load is, and you put the moment, and then you do your analysis based on the fact that you replace that wind load with the moment that would be causing at the end, and that's the situation you have there. So these represent, or these are very, very useful formulas that can help you analyze situations that normally occur without having to spend, like I said, $4,000 to $5,000 on a software. And the diagrams are pretty light, but like I said, you have to make sure your diagram, the reaction areas, the load pattern, the loads, everything else have to correspond to the diagram in order for you to be able to use these equations. And I think I gave you quite a few of them. I think I copied these right out of my wood handbook. Okay, and here, of course, if I happen to have a concentrated load at the end, and so on. Now here, if I happen to have an overhang, okay, so overhang beams, which is very typical, okay, and how to use these if I happen to have an overhang, if the load is only on the overhang, if the load is completely on the other side. So remember, by the principle of superposition, for example, you can, for example, if you only have, okay, and then of course you have a concentrated load, okay, if it's on the overhang, if you have a concentrated load in the middle. Now, if you have a situation where you have a concentrated load in the overhang, you have one in the middle, we'll use this one to calculate the overhang, this one to calculate this one, and you combine them together. That's the nice thing about superposition, that if I could literally break down my loads into each one of these diagrams and then sum them all up and get my final results. And that's what we're going to be learning how to do today. And again, okay, moments at each end and so on and so on. And here again, this is good. This is like if you have one concentrated moving load, you know, like this is when you're doing bridges, this is how you analyze bridges. You take a moving load and you try to calculate where the maximum shear would occur. And of course, this is like one axial load on your beam of your bridge. And this when you have two axial loads, in other words, you have the truck that has two axial loads and it's going across your beam. So these are like for, you know, moving loads. So they even have them for moving loads and so on. And of course, last but not least, when you have a continuous beam over 3 spans, if you want to be able to, if you only have it on one side, if you have a concentrated only on one side, and so on and so on. So you can do this even for continuous beams, okay? And of course, like I said, if I happen to have it, and there you go. So these are the beam formulas, and like I'm going to be sending you all of this, so you'll have this in your file. So these are the formulas that are very, very useful to do some very simple analysis. And now for, in our case, what we've had for the very first one is that we had a simply supported beam, okay? We had a simply supported beam here like this, and we had a uniformly distributed load going right across it. So therefore, if I want to calculate the deflection at mid-span here, which is at the center, well, there is a formula that I need to calculate that deflection. Okay, so that's what I'm going to use to calculate the deflection. This is the moment, but if I want to calculate the deflection at mid-span, here's my formula. So I'm going to take that formula, and so here's my formula. So the first deflection caused by the uniformly distributed load is equal to 5WL to the fourth. L always represents the span. E is the modulus of elasticity, and I is the moment of inertia. EI together is called the stiffness of the beam, and the higher the EI value, the stiffer it is, the less it's going to deflect. So that's what the EI is. So now I have all my values, so I simply have to plug them in. Now, be careful about your units. That's very important, because here I have now kilonewtons per meter is the same as newtons per millimeters. So therefore that doesn't change. I mean, that still changes, but I don't have to do anything regarding the value here. Remember to put the span in millimeters, okay, to the fourth. And of course, and then of course this is an MPa, and at one, I don't know if you remember, but 1 MPa, an MPa is a Newton per millimeter squared. That's an MPa. And of course, moments of inertia are always to the fourth dimension, always to the power of 4. So therefore, that cancels that. This will cancel this. This will cancel this. This will cancel this. This is in the denominator. We'll go back up in the numerator, and therefore I'm in millimeters, and that's the right units for deflection. And therefore, if I do the math correctly, I end up with a deflection of 20.2 millimeters here. So the first deflection caused by the uniformly distributed load is 20.2 millimeters. Is everybody okay with this? Do you have any questions at this point?
No, sir.
Thank you. Okay, if there's no questions, then we'll go on. So now, so that's the first deflection. Now I want to go and calculate the second deflection. So the second deflection, okay, here's my deflection. I mean, sorry, here's my load. I should say, here's my load. But remember, I'm not want to calculate the deflection caused underneath the load. I'm trying to calculate the deflection at midspan here, which is, you understand, at midspan. So in other words, at 3,000, caused by this load. So that's why I have to be careful that, because I've calculated the one by the concentrated load here at midspan, and then I want to add the same value always in the same location of the beam where I'm doing my calculation. So I want to calculate the deflection here, not underneath the load, at midspan. So I can add the midspan deflection caused by this load, and I can add the deflection at midspan caused by that load, and the two of them added together will give me the total deflection. So that's something I have to be careful about. So now, when I look at this and I say, is there a beam diagram that corresponds to this? In other words, do I have a beam diagram that has, you know, this is my beam. Okay, do I have a beam diagram that has, oops, sorry, I should have done it the other way. Okay, let me erase. Okay, is there a beam diagram that allows me to put no, I don't want to do that. Erase. Oh. Like I said, I should just draw it. Okay, so is there a beam diagram where I have a concentrated load here, P? I have, you understand? And it's not centered. And of course, that's what I'm looking for. Okay, so what I'm going to do now, so I'll go to the beam formulas and look for a diagram that corresponds to what I'm doing here. Okay, so if I go down, this is no good, this is no good, this is no good. Well, this is no good, that's no good, that's no good. Oh, that's no good because it's right in the middle. I don't have mine in the middle, but this looks good. In other words, I have one concentrated load, it's not in the center, and I have two reactions. So this is where I'm at. Okay, so now I'm gonna, okay, so this is where I'm at. This is the situation. I have simply supported beam concentrated load at any point. Okay, now I want to calculate it. Now here it tells me delta A at point load. So if I need to calculate the deflection right here underneath where the load is, I can use this equation here. But that's not what I need right now, because what I want is, I don't need to calculate deflection underneath the point load. I want to calculate deflection at midspan. So midspan goes from there to there, and therefore this becomes my x value. So my x value now is half of L over 2. Okay, that becomes my x value. And if I look at my diagram, it says that when x is less than a, in other words, if the load happens to be applied at a distance a, which is less than where I want to calculate, then I'm allowed using this formula here to calculate the deflection at x. And in this case, my x value happens to be L over 2, okay? And that's midspan. So therefore, I know I can use this equation here because the x over a value is correct. I'm calculating the deflection where the value of x is less than the value of a, and therefore I can use this equation here, okay? So here you got to, all it says is that I take my concentrated load, P, and multiply it by the value of B. B is the distance from the reaction on the right, okay, or R2. This is the B value, okay, so whatever that is. And then I multiply by the where I want to calculate my deflection. I want to calculate my deflection at L over 2, which happens to be x is equal to L over 2. That's where I want to calculate my deflection. And after that, the L is a span, B is a span, X is L over 2, E is the modulus of viscosity, and then I is the moment of inertia. And of course, I multiply that by L. So here's my equations. And therefore, I can go back and write that equation. Okay, so I have P is my concentrated load, B is the distance. Like I said, here we have a distance of 6 meters. Okay, and we want to calculate the deflection at mid-span. So this is 6 meters or 6,000 millimeters. I want to calculate at mid-span, which happens to be 3,000 millimeters. And therefore, that's the value of x. And therefore, since x is less than, this is the value of A here, this is the value of B. Since x is less than A, I can use the equation. Okay? So I got to make sure I conform to everything that is that is said in those formulas. I have to conform to the restrictions. So here's my x value. I'm okay. Now, the only thing you have to be careful about here, of course, is always the units. That's where people tend to, you have to remember that this is in kilonewtons and this here is in newtons. So therefore, if I want to be able to cancel, I got to convert the kilonewtons into newtons. So I got to multiply that by 1,000. Okay. Now, B, of course, like if we go back here, this was B. We want to calculate deflection here at a distance x from this reaction. So this here is x. So that's 3,000. The value of B here is 2,000. And of course, L always represents the span in these formulas. So L here is 6,000. So B is 2,000, X is 3,000. Now here it is L squared, B squared, X squared, okay? And then of course, here I have 6 EIXL. Now if you look, that, of course, because I multiply by 1,000, that becomes 30,000 Newton. That cancels that. Excuse me. This and this will cancel this. This will cancel this. I end up in millimeters. So all my units work out. Since I worked out my units, I'm going to now go through the trouble of doing the calculations. Guys, if your units don't work out, don't bother calculating. It's going to be wrong. So you're wasting your time. And these calculations can take you a few minutes, you understand? Because you have to take this, subtract this, and multiply this, divide it by that, and so on and so on. So now I've done this, and if I've made sure that everything works out correctly, I calculate my deflection. So the deflection at mid-span caused by this concentrated load gives me 6.8 millimeters. Now, I can simply, since I calculated exactly the deflection here caused by that load, and I calculated the deflection caused by the distributed load, I can now add the first deflection to the second deflection to get the total deflection caused by these two loads. And therefore, I take the first deflection and the second deflection. So in other words, I take delta 1 plus delta 2, 20.2 plus 6.8, I get a total deflection of 27 millimeters. And that's what's nice about the superposition, is that if I can break down each diagram into the loads that I see in the beam diagrams, I can take those values, I can take those formulas, I can calculate my values, and then by superposition, I can superimpose all those values one on top of the other and just add them up, and that will give me the total answer. Does anybody have any questions? Are we good? Or is it not clear what we just did?
It's good.
It's good? Guys, don't be shy. Now's the time to ask, because you're going to have a typical problem like this on the exam. So you might as well tell me now. And of course, I'm going to give you an assignment that you're going to have to practice this, but now's the time to ask. Okay, now I'm going to do another one, and I'm going to do it in imperial. Imperial, there's slight changes that you have to worry about in imperial, and I want you to be aware of those so that you don't make a mistake when you're doing something in imperial. So here is, okay, same thing. Okay, we have determined deflection at mid-span for the steel beam. The uniformly distributed load does not include the self-weight of the beam. The weight of the beam is to be added to the, okay, the steel beam is a W12 by 14. with a moment of inertia of 89 inches to the fourth, and the elastic modulusicity is 29,000 kips per square inch, or it's 29 million pounds per square inch. Okay, so it all depends. Now, in imperial, of course, this represents still a y flange. So that represents a y flange. That's number one. So that doesn't change. 12 represents that this thing has a depth of approximately 12 inches. But the 14 represents that this thing weighs 14 pounds per foot. So each foot of beam I have, so here, if I want to know the total weight of this beam, I take 16 times 14. It will tell me how much this beam is going to weigh, the whole weight. But okay. So the nice thing about the imperial system, I'm not working in mass that I have to convert into a force. The 14 pounds is already a force, and therefore I can just simply add it directly to my force, okay? So that's the difference in imperial, is that this is already pounds per foot, and pounds in imperial is already a force, and therefore I can add. Now, of course, pounds and kips are not the same. I hope you all know that there's 1,000 pounds in one kip. Does everybody know that, or is that completely new to everybody? So now, calculate the self-weight of the beam. Well, it's very simple. I got 14 pounds per foot. I know that, I don't know if you guys know this, but 1,000 pounds is equal to one kip, okay? A kip is, using 1,000 pounds at a time. That's why we have a kips, because when you're talking about very heavy loads, it's easier talking kips than it's talking pounds, especially when you're doing bridges. Everything is done in kips, thousands of pounds. So that's where, so in other words, I take the 14 pounds per foot and I convert it to kips per foot. I simply divide this by 1,000, 1,000 pounds per 1,000 pounds per kip, and therefore I get kips per foot. And clear. So that's it. Now, add the self-weight of the beam to the uniformly distributed load. Of course, I have 0.3 kips per foot. Now, the thing is that when you're doing things in imperial, you should always work in inches. So therefore, you should convert your kips per foot to kips per inches, okay? Otherwise, you're going to run into a problem when you're going to be doing all your calculations. So I do suggest that once you add your kips per foot, convert it right away to kips per inches. There's 12 inches per foot, okay? So 1 foot has 12 inches, and of course that cancels that. I end up with kips per inch. I simply divide this by 12, and I get my kip per inch. So that's the thing about imperial. As opposed to metric, where you have kilonewton meter is same as newtons per millimeter, but kips per foot is not the same as kips per inch. So because there's 12 inches in a foot. So keep that in mind. Okay. Now, so this is what I have. I have a beam that is going to be simply supported. It's going to have a uniform distributing load going across the whole span, with the load being 0.252 kips per inch now, like I said, because I want to keep everything in inches because I want my units to work out. And when I put in my span, I will also put the span in inches. So I keep everything in inches, and therefore I'll be able to end up with the right units. So my L is 192 inches, and my W is 0.252 kips per inch. So that's one thing I need to make sure of. Now, of course, determine the effects caused by the distributed load. And of course, if I go back to this one here, we've seen this before, but I'll go back anyways. So we are looking at the very first diagram, which is the most common situation that we're going to have. Okay, so therefore we have W always represents the uniformly distributed load, L always represents the span. And since we want to calculate it at midspan, we know that the maximum deflection will occur at midspan. So delta max at the center, it even tells you the center is 5WL to the fourth over 384 EI. So it's exactly the same equation that we're going to be using as we used before. That doesn't change whether you're doing it in metric or imperial. You just have to be careful about your units. So I'm going to use exactly the same equation. So I use 5WL to the fourth over 384 EIX. Now, again, guys, you just check. That cancels that. Inches to the fourth cancels inches to the fourth. Inches cancels inches. This, and therefore we get inches. So therefore we're in the right units. And if somebody please double check this calculation to make sure it's correct. I might have made a mistake, so I'd like if somebody would just double check it. So 5 times, and as a matter of fact, you should practice to do this. Don't forget to bring this to the fourth, okay, and then divide by 29,000 by 89. So this will give me a deflection of 1.73 inches. Oh yes, guys, when you're doing things in metric, okay, and you're calculating deflections, please, okay, 1 decimal place is ample. I mean, 0.1 of a millimeter or 0.7 of a millimeter, that is ample, okay, for precision. And when you're doing it in inches, 2 decimal places is ample. Don't go to 3, don't go to 4. That is accurate enough for deflection, okay? So do yourself a favor. Do not bring this to 3 or 4 decimal places. Don't bring this, especially when you're in metric, 1 decimal place is ample, imperial 2 decimal places is ample, and that's all you need to do. So there's my deflection here caused by this load. Like I said, because I put this in inches, everything works out, okay? And because I put this in kips per inch, everything works out. So the units are very important, okay? Does anybody have any questions before I move on? It's all good?
Yeah.
Okay. It's all good. We'll keep going. Now, so determine the deflection caused by the concentrated load. Okay. So here we go. Okay. Now, you'll notice that in this case here, okay, what happens is that I still want to calculate the load at midspan because that's where I want to calculate the load created by this concentrated load. But what happens here is that if I go look at the beam diagram, okay, I'm only allowed using that delta at x when A is greater than x, okay? So if I go look at the beam diagram, okay, that means that I do not conform to that requirement. And therefore, what I do is I simply take the mirror image and I make this the A value and I make that the B value. And by doing that, now my A value is greater than my X value because this also here is X, okay? And therefore, because I switch these around, I can now still use the same formula. Okay, so what's nice about this is that if I take the mirror image of what I'm looking at, and as long as I'm going to also mirror image whatever is corresponding to that, I can still use the formulas. So when I go to this, when I go to the formulas here, okay, I still have this situation here. Okay, I have a concentrated load here, but in order for me to use this formula here, X, I can only use this when X is less than A. Okay, now my load is here on my diagram, and therefore this is my X value. Okay, and in this case, and this is my A value, and this becomes my B value. Since A is less than X, I wouldn't be allowed to use this. Now, if I reverse them, in other words, if I make this my A value, and I make this my, I'm sorry, yeah, I reverse them. Okay, so I make this, like, this is my B value, this becomes my A value, okay? And I'm looking here, this is my X value, this value is the same as this. Now, my A value is greater than my X value, and therefore I'll have to make sure of that this is the value I use for B in the equation. So that's the only thing I have to do, okay? And that's why I'm still allowed to use this one as long as I make sure that the B value is always a smaller value where the concentrated load is. Is everybody confused, or is that clear? Okay, so there's no questions, and I'll just go on. We'll hope for the best. Okay, so here what I'm saying is that I have exactly the same diagram, except that, like I said, here, this is also my X value. I'm calculating this, which is 96 inches. Okay, and like I said, now my A is greater than my X, therefore this becomes my B value, and that's the value I use here in the equation. And if I do that, I am conforming to the restrictions given in that formula, and therefore I can use the formula. So that's what I'm going to do. Clear all. Okay, so that's what I'm going to do now. Now here, guys, like I said, units, very important. I got 10 kips. This is kips per square inch. I got nothing to worry about. These are all in inches. Okay, so excuse me. Okay, so excuse me. So I have the kips cancel. This cancels this. I'm sorry, kips. This, and this cancels this. This ends up here, and therefore I have inches. Great. So I know all my units work out. Okay. In other words, inches squared gives me inches to the fourth, and that will cancel that. This kips per inch squared cancels this inch. This is in the, below the denominator, it goes up to the numerator, and therefore all my units work out. Fantastic. We're good to go. And therefore now I'm ready to do the calculation. If I do the calculation, this deflection ends up being 0.52 inches. So now I've calculated deflection caused by the distributed load, and I calculated deflection by the concentrated load at the same location where I calculated, let's keep this in mind, at the same location where I calculated deflection by the distributed load, and therefore, since I'm doing everything at the same location, I can superimpose everything and now calculate the total deflection caused by both the distributed load and the concentrated load, just like we did before. So in other words, now I can calculate the deflection from delta 1 plus delta 2. I end up with 2.25 inches squared. Is that good enough? Does anybody have any questions?
So like, let's say there's multiple loads, we would just do the same for all the other loads and add them.
Well, exactly. Like, in other words, as long as you like, what, excuse me. Just I had a sip of water, went down the wrong way. So for example, let's say I have, here's my beam. Okay. Here's my beam. And here's my beam. I have a uniformly distributed load across here, like this, okay? And I have two concentrated loads. Fair enough? Two concentrated loads. And these concentrated loads are evenly spaced from the ends. You follow what I'm saying? Right? So if this is my situation, then what I can do is I can go look for a beam diagram. I can go look for the beam diagram that has the uniformly distributed load, which is what we've seen so far, right? And take all the values from there, and then go look for another beam diagram where I have two concentrated loads that are equally spaced from the reaction areas. And so if I go back to the beam diagram, so I would definitely use this diagram here to calculate for the uniformly distributed load like we've done so far. Okay. And if I wanted to calculate deflection at the middle, I would calculate it for this one. And then after that, for the other one, if the loads are equally spaced, then I look for a diagram that has two loads that are equally spaced, and I would use this diagram here. Okay, and from this diagram, if I wanted to calculate the maximum deflection, I would use this formula here. And therefore I would add, and that will give me the deflection at the center. Now, if the loads weren't equally spaced, like from the ends, then I would use this diagram here. You understand? I have this choice here. Okay, and then if I want to, and then it becomes a little bit more complicated. So as long as I can find a diagram, and then if I have loads that are not equal in magnitude, in other words, I have one load, one P1, one P2, and then I could use this diagram and so on. Okay, and then of course, so sometimes you can have diagrams where they're both combined, and then ultimately, for example, if I happen to have, for example, if I can't I can always break it down into as many diagrams as I need, and then I can just keep on superimposing and keep on adding each value from each diagram, and at the end it will give me the total result. Like now, just to show you, for example, clear all drawings. Okay. So for example, if I wanted to, I know that you guys, maybe you don't believe me, but so let's say I happen to have, now that's for deflection, right? But let's say I happen to have this here. Okay, I have a uniformly distributed load here like this, and I have a concentrated load at this point here. Okay, or I can even have another one here. Let's put two of them, for example. Okay, now let's say here I have 10 kilonewtons per meter, and let's say I've got a 5-meter span. Okay, and this is, let's say this is 10 kilonewtons each. Let's just make it 10 kilonewtons, 10 kilonewtons. Okay, now I know that I can go ahead and calculate my reaction and do my shear diagram and then do my moment diagram and get the maximum moment. But if I wanted to, I can look at what's the maximum moment caused by this load here. So I know that this is equal to WL squared over 8. That's the maximum moment caused by this load here. So therefore I have 10 times 5 squared over 8. That's the maximum moment caused by that load. And if I go down to this diagram here, where I have two equal loads, and I want to calculate the maximum moment, okay, maximum moment at the center, I can use this equation here, calculate the maximum moment at the center. I add them together, and I will get the same value as if I would do my moment diagram. I'm not going to do it, but so therefore, the way it applies for deflection, it applies for moments, it applies for shears, and you can, so for example, if I want to calculate, if I calculate the reaction here, well, the reaction here is simply equal to P, okay, and then the other one was WL over 2, therefore I add my P and my W, and I will get the total reaction, and so on. So that's, I mean, I can use these things to do whatever I need to do, and where these things are very useful is that it really simplifies your life, like to calculate your maximum moments and so on, so that you don't have to go ahead and do shear diagrams and moment diagrams for a whole bunch of things. And especially when it comes to deflections, they're very, very practical, because calculating deflections by the long way is very long. So these are very, very useful. This is a very, very useful piece of information that you have here. And I gave you, I think, 14 pages of it, or you're going to have 14 pages of it. And, and this is like I said, if you ever buy a handbook, all handbooks have beam diagrams and formulas, and not all of them are exactly the same. This one I found was pretty decent because it gave you quite a few options. And there you go. You understand? So these are very, very useful. And now we're going to use the same concept, okay, that we learned here, but we're going to apply it to help us analyze continuous beams, okay? So now, so what we're going to do now, I'm going to show you how you can apply the principle of superposition to analyze beams now, okay? So for example, okay, here we go. Here, calculate the reactions of the supports of the beam using the principles of superposition. So I can show you how you can use this to even analyze something that you wouldn't be able to analyze because this is not statically determinate. Why do we say that this is not statically determinate? If you remember from week number 4, at a pin, I have 1 unknown, okay, 2 unknowns, I have 3 unknowns, and I have 4 unknowns. As soon as I have more than 3 unknowns, I can't solve this by simple statics. There's no way I can solve this by simple statics, okay? It's impossible. So therefore, I would either have to go and find a way to do it, you know, or, I mean, I can go and buy some software. For example, you can go out and buy ADA. And, oh, speaking of ADA, did you guys receive an email from Great Tech?
Yes, sir.
Yeah.
You know,
What's that, sir?
you know, I hope you guys realize that I asked them to send you each a license that you can download ADA and have it on your computer, okay? That license is going to be good for a whole year. So has anybody bothered downloading the program?
Yeah, I downloaded it.
You did?
Sorry, sir,
Okay.
I don't receive the email.
You haven't received the email.
No.
You had to receive the email. You must have thrown it out. You might go check your junk mail because I put all your emails and I sent Great Tech all your emails, and Great Tech was supposed to send you all a license so that you can download ADA. And I do strongly recommend that you download ADA because sometimes if you want to, you can use the ADA in the -2H27, fair enough. But sometimes that lab is, there's a lot of people that are using it and you might get bumped off, whatever it is. So to be completely independent of the lab, I asked Great Tech to give you guys all a license, and that's what you received. So we will be using ADA in about 2 weeks from now. So I strongly recommend that during the spring break, download ADA on your computer. You've got the license there. Who said that they've already downloaded it? Yavor, you did?
Yeah.
And how did you open it? Is it working?
Yes, well, I didn't like use it, but I just downloaded it.
You download it, but you've got the serial number and you got the key to open it to start to.
Yeah, and it's
Okay,
like a license and everything.
Yeah, you have the license and the serial number, right? Okay. And you should have all received one because I sent all your emails to Great Tech, and I strongly recommend, because I think it's even starting on the second test, one of the questions you're going to be able to do it on ADA, okay? And the last test that we're going to have is completely on ADA, okay? And I'll tell you right now, guys, if you're going to rely on using the ADA in -2H27 through VM Horizon, that's your choice. But if there's a bug because you can't get in or you cannot use it because there's too many people using the software in there, because I think there's only 50 licenses, I will not use that as an excuse for you guys not to be able to do the exam. That's your risk. You can do whatever you want. I purposely went through the trouble of requesting licenses, and I expect everybody to have it on their computer. So this way we are completely independent. I've got my own version on my computer. I can go to -2H27 like everybody else, but not to have that issue of having too many people going there at the same time and not being able to have access. I strongly recommend you all download ADA, and and if ever you don't have a license, send me a Mayo. I will tell you the person that you can, you're gonna have to apologize because she probably already did send you the license, and you probably go look in your spam, look for Great Tech. The person that sent the email, her name. Anyways, it's Great Tech, the company. So keep that in mind. I should have told you this before, that I'm going to be requesting licenses, and please, when they come in, do not throw them out. Keep them, because it's, like, you're going to be able to use the program for a whole year on your own. And that to me is a plus. So I'm going to repeat this again at the end of the class, but keep that in mind. Okay, so now if we get back to this problem here, okay? So if I had to solve this problem and I did not have a software to help me solve this problem, okay, I can use the principle of superposition to solve this problem. And how would I do that? Well, I would simply, well, what I would do is I would remove this support here, okay? And basically, I would remove the support. And what happens now to the beam? Is that what happens to the beam if I remove the support?
I think so, yeah.
Okay. Now, if I remove that support, what's going to happen to this beam? It becomes longer, right? Right? You agree?
Yeah.
Can I calculate the deflection caused by this load?
Yes.
Okay. Can I actually calculate the deflection caused by this load right where I took off the reaction? In other words, the deflection right here. Can I
Yes, we
calculate?
can.
Pardon?
Yes, by using the formula.
Exactly. So using the formula, I'm able to calculate the deflection right where I remove the thing, right? Agreed? Now, if I take the same beam here, if I take the same beam here, okay, take the same beam here, and I apply a force P here, and if I can calculate, can I calculate the deflection caused right underneath the force by this force P? Can I do that with the beam formulas?
Yes, we can.
Yes, we can, okay? So in other words, if I can calculate the deflection here, now, if this deflection here, okay, is equal to this, if the deflection 1 here is equal to the deflection 2. You understand? If I can calculate the deflection here by this force here and make it equal to this deflection here, right? Everybody understands what I'm doing? So if I apply a force P going upwards here, will that bring the beam back up to straight? In other words, if I apply a force P going here like this, will that make the beam straight again?
Yeah.
Okay, so P becomes your reaction. So you already solved for your reaction. And now that I know this reaction, I can go and solve for that reaction. I can go and solve for that reaction. So you see how you use the principle of superposition? By the deflection caused when I remove the support, if I can calculate a force that will bring that deflection back to its original position, then I know that that force is going to be equivalent to what the reaction would be if that support is there. Isn't that convenient? I don't know about you guys, but when I saw this the first time, I thought the guy that thought about this was pretty smart in my books. So now, so what we're going to do is, so convert the continuous beam to a simply supported beam by removing the support between it. Okay, so I'm going to remove the support. So what I'm going to do is this is what I have. Okay, so now all of a sudden I have an 8-meter span, no longer 2 spans of 5 meters and 3 meters. I have an 8-meter span. And what I want to do is I want to go and calculate the deflection caused right where I removed the support. In other words, I want to calculate what that deflection is. So what I do is I go calculate the deflection where the support was removed. So I come here and I look at this. So I go to my beam formulas. And this is exactly what I have. I have a simply supported member with a uniformly distributed load across the whole thing. Now, out of all of these, which equation will I use?
Would it be the last one?
Very good. And why would we use the last one?
Because the deflection isn't in the middle.
Exactly. In other words, this equation here allows you to calculate the deflection anywhere along the beam. Everybody follows? That's what this equation does. In other words, if I want to calculate the deflection right at this point here, I can put a value of x equal to that, and I can use this. It will give me the deflection if I want to calculate the deflection. So I can calculate the deflection anywhere along the beam based on this here. As a matter of fact, if I take this formula here and I put x is equal to L over 2, guess what happens? What do you think happens when I put x is equal to L over 2?
It would be as if it was in the center.
And that, if I substitute in here, I'm going to get exactly this equation here. And if you don't believe me, this is L over 2 squared, right? So this gives me L squared over 4, and you keep going, and when you cancel replace all the L, this will give me, you understand, this is L over 2 cubed, therefore this is L over 8 cubed. 8 times 4 is 24. And then, okay, and then here I have L over 2, so 20, and therefore I would get exactly this equation here. So that's why we use this one when we calculate midspan, because it's much faster. But I can use this equation to calculate my value of, okay. So right now my support is here, and therefore this becomes my value of x here, okay. And therefore I can go and calculate deflection right at that point there. So, okay, so here we go. So now, so I have delta x is equal to wxl cubed over, okay. Now, remember, okay, where w is 15, x is 5 meters, and L is 8 meters. Okay, in other words, if you want to see this, it's simply what you're doing is you're doing this. Okay, you got a concentrated load here. We know that the span here is 8 meters. Okay, I'm sorry, we want to calculate it at a distance of 5 meters here. I shouldn't put the concentrated load. Like this is 5 meters. This becomes 8 meters. Okay, so x is 5 meters, L is 8 meters, and of course, the load was 15 kilonewtons per meter. Now, so I put everything into the equation, okay, and I simplify it, and I put delta x is equal to 17,755 kilonewtons per meter cubed. Why did I put per meter cubed? It should be meter over. I think this is, oh yeah, meter cubed. Sorry, it is meter cubed. Okay. Okay, so that cancels that. Oh yeah, it's kilonewtons per meter cubed. I'm sorry, my mistake. Now, so now I have, this is one equation. In other words, that's the value of delta x at that point. Now, determine a concentrated force that would cause an upward deflection where the support was removed. Okay, so what you want to do is you want to calculate a force here that will give you a deflection here that will be equivalent to the deflection caused by the distributed load. So that's P, okay? So now what do? I go to the beam formulas, okay? And I go down, and although it's acting underneath, I don't care. I can use the same formulas, okay? Just have to remember the direction. So I've got this here, right? A, B, I got the value of P, okay? So in other words, P is going upward. So therefore, and of course, the value, now I don't have to worry about X. I want to calculate the deflection where the load is being applied. So delta A, okay, the deflection at what they call here A, at the point load is equal to P A squared B squared over 3 EIL. So that's the formula I have to calculate the deflection cause right where the point load is being applied. So therefore, that's what I want to use. So therefore, this is, okay, the only thing I need to know here is, of course, the A value, which is 5 meters, the B value, which is 3 meters, P, I don't know, that's what I'm trying to solve for, and the EI, and I know my L is 8 meters, okay? So I'm going to use that equation. So I use delta A, okay, is equal to A squared, B squared, okay? And like I said, this is the value of A, this is the value of B, P, I don't know, okay? But L is, of course, this is L always represents the span. So I have A is equal to 5 meters, B is equal to 3 meters, L is equal to 8 meters, okay? To keep it simple, I put everything in the equation. I go P is equal to A squared, meter squared, B squared, meter squared, okay? Now, now I know that, okay, that del at A, if I simplify this, I get, I'm sorry, this thing keeps popping up on me. I can't see what's written there. I'm waiting until it goes back down. So I get 225 m cubed over 24 EI, and that's equal to P. Now, like I said, if you look at this, okay, if you look at this from the displacement at a support is 0. In other words, there's no displacement. In other words, it's supposed to stay where it is. It doesn't go down, it doesn't go up. That's what you always, you know, get when you're doing an analysis, that you at the support, it's always displacement is 0. So that means that the displacement upwards minus the displacement downwards has to be equal to 0. So what you're actually saying is that the deflection caused by the force at A and the deflection caused at X by the distributed load, they should be equal. In other words, the deflection going up and the deflection going down have to be equal. And since that's the case, you know that this is the deflection caused at the concentrated load. This is the deflection caused by the distributed load at that point along the beam. And therefore, I can equate this to this. So therefore, I put everything in terms of P. So I get P is equal to 17,775. Now you notice here, guys, the reason why I don't need the EI, because this and this cancel this and this cancels that. So right away, when I equate this side to this side, I simply get this part here divided by this, okay? And of course, what's nice about it, this cancels, that cancels, I end up in kilonewtons, and therefore the value of P is 79 kilonewtons. And that's really nice. So that means that right now, this is what happens. I have an unknown there, or I have two unknowns there. I have, this one now becomes known. This is 79 kilonewtons. And I have an unknown there, okay? And I have, of course, a uniformly distributed load. Now I have three unknowns, and therefore now I can use simple statics to finish solving my problem, because I solved for this unknown using the principle of superposition. So now this is exactly what I have. I have Lx, Ly, Ry, and of course I've solved this to be. Now guys, be careful when you do this, okay? There is no way of checking if this value is correct by doing the sum of f of y, because if you put the wrong value here, your sum of f of y's are always going to work out. So unfortunately, you got to be absolutely sure that you did this correctly and you put the right reaction force here in order for the rest of your problem to be corrected. It's not like the other way I showed you the 2 weeks ago, that you can do moments about one end, moments about the other end, take the sum of f of y to make sure it all balances out, and then you know you're in the right track. It doesn't work for this particular solution, okay? So you got to be very careful. Now, of course, if I take the sum of f of x, so I know that that's 0. Okay, that's how I know why it's 0, because the equation of equilibrium tells me it's 0. Now, like I said, I can solve for Ly, I can solve for Ry, whichever one, okay, whichever I want. Well, I don't even remember what, I took moments about Ry, okay. Now, guys, like I said, I hope you guys are starting to get a little bit more comfortable. This is, you took counterclockwise to be positive, okay? So therefore, first thing I worry about is with respect to Ry, this is going clockwise. Therefore, I first worry about the sign. Then I worry about the force. Well, I don't know the force. The force is Ly. And then I worry about the distance. So it's always the sign, the force, the distance, the sign, the force, the distance, the sign, the force, the distance, okay? So therefore, so here I have minus Ly times 8 meters, that's the distance. Now I can take this as being just one distributed load. Therefore I take 15 kilonewtons per meter times 8 meter. This gives me well, first of all, I have to worry about the sign. So it's going counterclockwise, therefore it's positive. Then I worry about the force. So it's 15 kilonewtons per meter times 8 meters. This gives me the force. And how and where is it acting with respect to the points I'm taking moments? About halfway over. Okay, so it's 8 over 2 meters, and that's going to be that. This, of course, I worry about the sign. This is going this way. It's going, excuse me, clockwise. Therefore, it's negative. What's the force? 79. What's the distance? 3. And for me to have equilibrium, of course, that has to be equal to 0. So now I do that. I solve for Ly, I get 30.4. And at this point here, you can do what you've been doing in physics, because it doesn't matter if you take moments about the other side, it will not help you to check if you have equilibrium, because this is a number that you actually put in. I can put here 82 or 41, and I can do this whole thing, and I can show you that at the end, it's always going to add up to equilibrium. So here I can simply do sum of f of y is equal to 0. So therefore I do 30.4 is this one here, minus 15 kilonewtons times 8, plus 79 is equal to Ry. And of course, now Ry is 10.6. So now I've got my 3 reactions. Here I've got 30.4 kilonewtons, and here I have 10.6 kilonewtons. And of course, from here, I can simply draw my shear diagram, okay? And then, of course, my moment diagram. So once I calculate my reactions, I can go calculate, do my shear diagram and my moment diagram. And of course, so remember, the shear diagram, guys, you simply say, is this going up with respect to the other one? So you take it as being a positive shear. So therefore, on my calculator, I would put 30.4. So I put, on my calculator, I enter 30.4, 30.4, and then I start. It's going down, so I go minus 15 times 5, and that gives me minus 44.6. So on my shear diagram, I'm going from 30.4 all the way down to minus 44.6, plus 79 because it's going up, goes up to 34.4, minus 15 times 3 equals 10.6. And of course, I go back to 0. So I know my shear diagram is perfect. Okay. And of course, for the moment diagram, I calculate this point here. This is the slope of the line. And therefore, I have 30.4. 30.4 divided by 15. So this is at 2.2 meters. 2.02 meters and so on, and therefore I can go calculate the moments where, okay, and that's how I do the shear diagram. So therefore Here's a moment, here's a shear diagram. Like I said, this is going up. The left side is going up with respect to the right side. It's positive, 30.4. And then this is going downwards. I simply subtract. And then this is the slope of the line. So therefore I can find where these 2 points are. And then of course, by the areas, I can calculate the moments. And of course, from this, I get my I get my moment diagram. And that's, and that's based on these areas here. So that value there is going to be that value there. That minus that gives me the value there. Then that plus that gives me the value there. Subtract that, I should go back to 0. And that's my moment diagram. And there's my moment diagram, okay? And once you've, like I said, once you've solved your reactions, then you can definitely come up with your shear diagram and your moment diagram. How are we doing time-wise, guys? Are we still, 11:25. Is that clear, what we did? Do you have any questions? Is everything okay, guys? Like, 'cause I think that's pretty well it for today. Like, let me just check. Yeah, so you're gonna have assignment due today by 5 o'clock. Okay, so the assignment's gonna go out at about 11:40. If you want, I can, no, I'll leave it at that. I'll leave it at 11:40, because what time is it now? 11, it's almost that time. And that's it. So do you guys have any questions? Do you want me to go over something, or is everything clear? I'll put this on pause.